You know, computer simulations are easily one of the most powerful tools we've ever created. I mean, they're everywhere. Designing our planes, forecasting our weather, they basically shape our entire modern world. But here's the thing. How much can we actually trust them? To figure that out, we really need to get a handle on what they can do, and maybe even more importantly, what they can't.
But really, the bigger question is, can we? We're about to dive into the absolutely incredible power of computer modeling. But we're also going to uncover the fundamental limits that draw a hard line between a simulation and a real-world experiment. And believe me, that difference is way more profound than you might think.
So first up, let's just take a moment to appreciate how ridiculously capable these models are. They are, and this is no exaggeration, a virtual proving ground for some of humanity's absolute biggest and most ambitious projects.
Just let that sink in for a second. We can use a computer to figure out the insane forces of a controlled explosion. An explosion powerful enough to literally escape Earth's gravity, all before a single piece of metal has even been welded together. I mean, that's the kind of sheer predictive power we're dealing with here.
Okay, so what you're looking at here is kind of a peek under the hood. This is how organizations like NASA are able to wrangle just mind-bendingly complex systems. Every single variable, every little component, every interaction, it can all be modeled, tested, and tweaked in this virtual sandbox. It makes engineering feats that would have been totally impossible just a generation ago totally achievable today.
So that brings up a really good question. If these simulations are so powerful, so accurate, what's the difference between them and a real-world experiment? Why do we even bother building the rocket at all?
And boom, there it is. This quote from our source material just gets right to the heart of the matter. If a supercomputer could tell you everything, why would we spend billions of dollars building something like a particle collider? Well, the answer comes down to a few really crucial fundamental differences. But look, before we get into those differences, it's so important to understand that these are not video games. The process for creating a professional-grade simulation, like the ones NASA uses, is just incredibly rigorous.
Now, from a bird's eye view, the process seems pretty simple, right? Step 1, you outline what you need the model to do. Step 2, you figure out if it's actually the right tool for the job. And then step 3, you build it and you test it. But that last step, that's where all the heavy lifting happens.
Just take a look at this. This flowchart gives you a sense of the insane detail involved. Verification, analysis, feedback loops, trade-off studies. This is not guesswork. It is a highly disciplined engineering process, and it's all designed to make that model as rock-solid and reliable as humanly possible.
And all that discipline? It's enforced by official standards. We're not talking about internal company guidelines here. These are industry-wide standards for systems engineering. It's all about ensuring that when a model gets built, it's done with the absolute highest level of professional rigor. So with that foundation laid, let's talk about the limits.
Okay, so we've established that these simulations are powerful, they're rigorous, but now we get to the core of it. What are those fundamental differences that put a simulation in a totally different category from a true experiment? Let's break down the 3 big ones.
All right, number 1, this first difference is honestly the most philosophical. It really gets to the very nature of what knowledge even is.
Okay, so here's the crucial distinction. A real-world experiment can totally surprise you. It can uncover new data from the universe that nobody ever predicted. It can generate brand new knowledge. A simulation, on the other hand, no matter how complicated it is, can only ever tell you the logical outcome of the rules and the data you already gave it. It's great at finding hidden consequences for sure, but it can't discover a new law of physics that wasn't already programmed into its code.
And that leads us perfectly into the second key difference, which is all about what exactly is being put to the test.
So in this context, the target system is the real thing. The actual car, the actual building, the planet. An experiment, like a real crash test, operates directly on that target system. A simulation, though, is always operating on a model of the target system. It's always one step removed from reality, and that is a massive distinction.
And finally, we have number 3. This is probably the most important difference of all, because it separates what a simulation can prove from what it simply can't. This is the mic drop right here. You can't use a simulation to prove a fundamental theory, let's say the theory of general relativity, if you had to program the rules of general relativity into the simulation to make it run in the first place. It's just a circular argument. The simulation's results are always going to reflect the assumptions you started with. Only a real-world experiment can truly validate or falsify a foundational hypothesis about how the universe works.
So, after all that, where does that leave us?
Well, it leaves us with a much more sophisticated way of thinking about this. It's not about saying simulations are good or bad. It's about knowing exactly what they are and, just as critically, what they are not.
The big takeaway here is that super rigorous process used by places like NASA creates unbelievably powerful tools for engineering and prediction. We just have to always remember that they operate inside those strict logical boundaries we just talked about. Real wisdom comes from knowing both the power of the tool and the edge of its capability.
And look, this isn't just some abstract academic debate. This distinction matters a lot when we use these models to make massive decisions that affect all of us. Whether we're talking about climate policy or deciding to ground every airplane because of a volcanic ash model or setting national economic policy, understanding the assumptions and the limits of those models is absolutely essential.
So, I'm going to leave you with this thought. We are constantly hearing things like the model says or the simulation shows. But now you know the fundamental difference between a simulation and reality. So the next time you hear that phrase, what's the one question you're going to ask about the model's assumptions before you accept its conclusions?